Hello and welcome to this short introduction to PLUMED. This video is designed to give you a flavour of the sort of calculations that can be performed with PLUMED and to show you how the input syntax works. Hopefully, after watching this video, you will understand things well enough to be able to jump in and read the parts of the manual that are relevant to the type of calculation that you would like to do. Those of us whose research involves performing atomistic MD simulations are lucky enough to work in a field where there are a number of very large and well-established codes that we can use. As a community, we owe the authors of these codes an enormous debt of gratitude, as for many of us, our ability to run calculations on the most modern and fastest computers is a direct result of their efforts. That said, there is a slight problem with this modern model for MD code development, where a small number of complex and carefully optimized codes are maintained by a small and technically skilled set of developers and used by a much larger community of users. New algorithms developed by users don't get implemented in all the codes, and as a result, these new ideas are not shared with the widest possible community of users. Worse still, any user who develops code and adds it to GROMACS, say, has to re-implement everything if for some reason he decides to use NAMD for the calculations in his next paper. We, the developers of PLUMED, suffer this problem with regards to the development of metadynamics and a number of other free energy methods. We each used different codes and eventually found ourselves with bits and pieces of collective variables and methods in each of the MD codes, and with no single MD code that had the full range of functionalities that we had developed. We thus took a decision in 2010 to combine all the bits of codes that we had developed over the years into a single separate piece of software that could be plugged into all the different MD codes used by the community. We called this new code PLUMED. This figure shows how PLUMED is interfaced with an MD code. Unsurprisingly, PLUMED is first called during initialization, that is to say before the main MD loop starts. When PLUMED is called at this point, the input file is read in and the calculation is set up. PLUMED is then called just after the calculation of the forces during every single MD cycle, and the atomic positions are passed from the MD code to PLUMED. This slide shows about the simplest thing that we can do as a result of this passing of the atomic positions between the MD code and PLUMED. This input instructs PLUMED to take the positions of the 4th and 10th atoms in the MD code's input file and to calculate the distance between them. The value of this distance is then printed to an output file called colvar on every 10th step of the MD calculation. The command telling PLUMED to calculate the distance and the command telling PLUMED to write the data to the file are separate. The data to print is referenced in the print command by using the label D1. This is the label that is given to the numerical data calculated by the distance command. This way of implementing the print command allows us to use it when we want to calculate and print different quantities. As an example, we can recognize that atoms 4 and 10 are connected by a vector, and that we can calculate the projections of this vector on the x, y, and z axes. We can calculate these projections by adding the keyword components to the distance command. This changes the D1 quantity that is calculated by this command from a scalar to a vector quantity. When printing, we can thus choose to print only the projection of the distance vector on the y-axis by using the command like this. Alternatively, we can print all three components of the vector by using the command in this way. If we don't want to calculate a distance but rather some other quantity, we can do so by changing the first command only. Here is an example where we are calculating and printing the angle between the vector connecting atoms 4 and 10 and the vector connecting atoms 4 and 42. We can even monitor more than one quantity at once by using a command like the one shown here. Let's now imagine that we want to calculate the distance between two diatomic molecules. If we think in terms of the individual atoms, then there are 4 possible distances to calculate. In this case, the distance between atoms 1 and 3, the distance between atoms 1 and 4, the distance between atoms 2 and 3, and the distance between atoms 2 and 4. What we might really want, though, is the distance between the two centres of mass of the molecules. We can calculate the positions of the centres of mass by using the COM command. These centres of masses can then be referenced in other commands by using the labels C1 and C2 of the two COM commands. We can thus calculate and print the distance between centres of mass that we require by using the following instructions. These calculations of collective variables are useful because we can calculate the free energy as a function of the CE and thus obtain physical insight into the problem of interest by taking the logarithm of a probability distribution function. We can calculate this probability distribution by calculating histogram as a function of our collective variables as we sample during the MD simulation. There is a problem with this approach, however. If there are high energetic barriers along our reaction coordinate, the probability of crossing them in a short MD simulation is very low. As a result, what we see is something like this movie. The system remains trapped in the vicinity of an energetic basin in the energy landscape, and there are no interesting barrier crossing events on the timescale of our simulation. We can resolve this problem, however. As shown in this second movie, we simply adjust the Hamiltonian for the system by adding some simple bias potential. This bias potential is designed to force the system to visit a part of configuration space that we are interested in, and generally it is expressed as a simple function of some collective variable. For example, it could be expressed as the distance between pairs of molecules or atoms. In the example input shown below here, the bias is a harmonic restraint, like that in the equation. This restraint acts on the angle between the vectors connecting atoms 4 and 10 and the vector connecting atoms 4 and 42. The potential has a minimum at pi over 4, and as a result forces the system to spend the majority of its time in configurations where the angle between the two vectors is close to this value. A bias potential does not have to be a static, time-independent entity. PLUMED also allows you to design bias potentials that force the system to move along a collective variable during the course of a short simulation. The input here, which uses the moving restraint command, tells PLUMED to do a 1,000-step calculation during which the angles between atoms 10, 4 and 42 is forced to change smoothly from pi by 3 to pi by 2. You can even learn how to bias the system based on what occurs in the past, by making use of the Metadynamics algorithm. In this example, a history-dependent bias potential is constructed in a manner similar to that used famously by Hansel and Gretel to recall their route home through the woods. Every 100 steps, a breadcrumb, in Metadynamics this is a repulsive Gaussian function, is added to the bias potential at the point visited during the early parts of the simulations. These functions force the system to move away from visited parts of configuration space and out into unexplored configuration space as shown in the movie. All this biasing of the dynamics is possible because of the second way in which PLUMED interacts with an MD code. At the end of the PLUMED calculation, any additional forces that arise because of bias potential are passed back to the MD code, so that these additional forces can be incorporated when the equations of motion are integrated. For more information on PLUMED, please look at the detailed manual pages of our website. In there you will find detailed instructions on all the functionality that is available in the current stable release of the code, together with tutorials that describe certain things that can be done with the code. This is an example of a tutorial that shows you how to calculate a minimum distance. If you feel that you've really had to struggle in getting something to work, please share your experiences and write tutorials for other users of the code. If you've downloaded the latest development version of the code, you should join the PLUMED 2 Git mail list and read the postings there. New features in the development version of the code may not be fully documented online, and you should get in touch with their developers through the mail list if you want to use them or if you encounter difficulties.